Alright guys, today we're going to be looking at all of the trig graphs that we have not used yet. So there's going to be tangent, cotangent, secant, and cosecant. So we're going to learn a couple new parent functions. The first one we're going to start off with is just y equals tangent of x, and we're going to graph this one in degrees, and again, just like we did with the sine and cosine parent functions, in order to see what my parent function is going to look like, I'm going to start by plotting some basic points. So I'll start with these three. So if I take the tangent of 0, the tangent of 0 is 0, the tangent of 45 is 1, the tangent of 90 is undefined. If I went backwards from 0, the tangent of negative 45, it's the same reference angle as 45, but in the fourth quadrant, tangent's negative. Then if I went to negative 90, that's the same as 270, but 270, the tangent of 270 is undefined. Alright, and then let's add one more. Let's do 135. So again, that would be the second quadrant. The reference angle is 45, so the tangent would be negative 1. So I can start by plotting a few of those points, but the problem is I don't really know what's going to happen when my graph is undefined. So what I'm going to do is I'm going to look at my graph as I get close to that undefined point. And I'm going to see if I plug it in some values in my calculator, I'm going to see what happens. So I'm going to go ahead and plot those points that we do know. And then let's look at our calculator. Okay, so let's see, as I get close to 90 from the left side, I can do the tangent of 89. And I get that value. So as I get closer to 90, that would be like the tangent of 89.9. Or I could do the tangent of 89.99. So as I keep getting closer and closer and closer, I can see those y values just keep getting greater and greater and greater. So now let's look from the right side. If I look at the tangent of 91, that's just to the right of 90. We get a negative value. Closer from the right side, like 90.1. And the tangent of 90.01. So you can see what's happening here is my graph from both sides is approaching a negative value. Oh, it's approaching more and more and more. It's going towards infinity or towards negative infinity. So what that means, you guys learned about this in Algebra 2, when my graph is going to go up and up and up and up and up like that towards infinity on one side, and lower and lower and lower towards infinity on the other, that means at 90, I have an asymptote. So that means everywhere this graph is undefined, I'm going to have an asymptote. And my graph is going to look something like this in between those asymptotes. Okay, so the shape of that line, it looks kind of similar to your x cubed parent function. And if this graph were to keep repeating, I would just have more and more and more of these sections. So there's a few major differences between this graph and my sine and cosine graph. Obviously the shape is incredibly different. But another major difference we have here is the distance it takes to repeat itself. So in order to complete one cycle, my period on this graph is actually only 180 degrees. Whereas before it was 360 degrees. So that is one major difference. Alright, if I look at my critical points that I'm plotting, the very first point at 0, so what will eventually be shifted, at 0 on this graph what I have is I have a center point. So I start with a middle point, then I have a higher critical point, and then I have an asymptote. And then I have a lower critical point, and then I go back to the middle, and then a higher point. So it follows that same pattern. So my critical points start in the middle, then become a high critical point. Not the highest point on my graph, but it is a higher point, then an asymptote. And then after the asymptote, I go to a low point, and I repeat that same pattern. Alright, so what we're going to look at is I'm going to show this to you guys on the calculator, so you guys can see what multiple cycles of y equals tangent of x looks like. Oops. Alright, so I'm going to go to y equals. I'm going to look at y equals the tangent of x. Alright, my window, I'm in degrees, which means my window needs to go at least to 180 in order to see some of this. But if I look at my graph, it says y equals the tangent of x. The bigger my window is, the more of these cycles I'm going to see. Alright, so the last thing on this graph I want to look at is what we originally, under sine and cosine functions, what we called our amplitude. It is a little bit different on these functions. So what we're still going to have is a vertical stretch in some cases, but it's not going to be really an amplitude because my graph is going to continue going. But what's different is this is still my vertical stretch. This height is still my A. So when I change my A, that's the height that I'm going to be changing. Alright, so the next thing we're going to look at is the cotangent parent function. And we're going to see what the differences are between cotangent and tangent. We're also going to do this graph in radians, so it'll be a little bit different. So I'm going to pick some easy radian values. Let's do 0, pi over 4, pi over 2, let's do 3 pi over 4, and pi. Now if you remember cotangent, that's the same as 1 over the tangent of x. So basically, I'm going to find the tangent of x, and I'm going to flip it. I'm going to take the reciprocal of it. Remember, reciprocal is different than inverse. So the tangent of 0 was 0, but the reciprocal of 0, so the cotangent of 0, is actually going to be undefined. The tangent of pi over 4 is 1, which means the cotangent of pi over 4 is 1 over 1, which is still 1. The tangent of pi over 2 was 0. However, it was undefined, but the cotangent is going to be the reciprocal of that. And the reciprocal of that is going to be 0. 3 pi over 4 falls in the second quadrant, so that's going to be a -1. And then pi, that's going to be the same thing as 0, and that's also going to be undefined. So we're going to plot these points now on my graph. And if you guys look, there are going to be a few similarities and a few differences. So first of all, we talked last time, when I have that 0, when I have that undefined value, that's going to be an asymptote. So one major difference already is cotangent has an asymptote at 0. And if you guys look back at the tangent parent function, the tangent parent function started with a center point. So that is one major difference, is I'm starting with an asymptote. Then when I plot those higher and lower critical points, they're still 1 and -1. But the first one is high after an asymptote. So this graph is actually reflected. It's the same shape, but it's going the opposite direction. And that's just because of those exact values of our parent function. So the pattern of my critical points here, my critical points, I start with an asymptote, and then I follow with a high critical point, a middle critical point, and a low one. And then I start all back over again with an asymptote. A few similarities though. The shape does look similar. And another big similarity, the period is still pi radians, or 180 degrees. So it still repeats itself just as frequently. And again, this would carry on, the same pattern would continue with that same pattern of my critical points. So that's one cycle of your cotangent parent function. All right, remember, the biggest difference here is cotangent starts with an asymptote. So what we're going to do now is we're going to look at that same equation that we looked at for our sine and cosine waves, and we're going to figure out what all these letters are for our tangent function. And what you're going to notice is a lot of them are very, very, very similar. So the first one we're going to look at is C. And just like C was my vertical shift for my sinusoidal functions, it is still the same thing for tangent. It's still the vertical shift, and it is still the y value, or the height, of all of my center points. So that is not changing. Then after C, my next value is A, and A on my sine waves was my amplitude. And again, slightly different. It's not really my amplitude, but we're going to call it the amplitude, because it is still the vertical stretch. It's still the distance between my middle critical point and the height of my high or low critical points. So again, still these first two functions, these first two letters, those are still vertical changes. Those still affect the y-axis. Okay, the major difference here, though, from my previous ones is the b. Okay, b is still what I use to find my period, but with sine and cosine functions, whenever I did b, I did 360 or 2 pi divided by b. But we just saw one period in that parent function wasn't 360, it's 180. Or it's pi in radians. So this is my major difference. So in order to get my period, I still do it the same way, it's just a different value at the top. And what's nice is to find my critical points, I can still do the period divided by 4. But what I do need to remember is that critical points include asymptotes. Asymptotes are critical points. And then the last one is D, and D again is very similar. Okay, D is still going to be a change, a phase shift, a horizontal shift. But what's a little bit different this time is what kind of a change it is, and it depends if it's a tangent graph or a cotangent graph, what I'm drawing at that point. So at the phase shift, at tangent, I'm going to plot a middle point, whereas cotangent, I'm going to plot an asymptote at the phase shift. And that's my major difference. Okay, so again, very similar things to what I did with sine and cosine. So now we're actually going to graph one of these and see what it looks like. Okay, so this is the function we're going to look at. This is in radians. So we're just going to identify what all those things are. The first things I'm going to start off with are my two vertical things, which I'm going to look at C and A. So my C, my height of my middles, is 3. That's my vertical shift. And then A, my amplitude, the height difference between my middle and low critical points is 2. So what that's going to allow me to do is I'm going to go ahead and be able to plot out my y-axis. I know my middles are going to be at 3, and then my high and low points are going to be 2 away from that. So I already have that done. So the next thing I need to do is I need to use what I have here. I need to use my b to find my period. So the period is going to be pi divided by pi over 8. So I flip the second and multiply. So that's my period. It will take 8 radians to complete one cycle, which means that I'll have critical points every 2. So my critical points are going to increase in increments of 2. And the last thing I need to look at on here is my phase shift, or my horizontal shift. And my phase shift for this graph is a positive 1. So at 1, I'm going to mark my first x-axis value. And because this graph is a tangent graph, at 1, that's going to be a middle point. So I'm going to go ahead and mark my my x-axis now. So I'm going to start at 1, and then I'm just going to count by 2s, because those are the increments of my critical points. And I'll go positive and I'll go negative, just so we can see a good picture here. Okay, so once my axes are all marked, all I have to do then is just draw my graph. So follow the pattern that I have for my parent function. And what my parent function did was the first critical point is middle, followed by high, followed by an asymptote. After my asymptote is a low critical point, middle, high, asymptote. And I'm going to continue this pattern on the other side. My next critical point to the left of 1 is negative 1. 0 is not actually a critical point. Well, there's another asymptote. Then I just connect my dots, and I get my tangent graph. So there is a fully graphed tangent function. Alright, so we're going to try one now as cotangent. And what you're going to see on this graph, it's actually going to make this one a little bit quicker. Everything on this function is the exact same as what I just did. The only difference is that it says cotangent. So that means that my C is the same, my A is the same, which means my y-axis is going to be the same. I'm still going to have a middle of 3, a high of 5, a low of 1. Alright, the other points didn't change either, so I'm still going to have a period of 8, critical points at 2, and a phase shift at +1. But what's different is that this graph is now cotangent. So at 1, instead of drawing a middle point, I'm going to draw an asymptote. So I'm going to go to mark my x-axis, just like I did in the other one. I'm going to start at 1, and I'm going to keep going, counting by 2s again. And I'm going to run out of space. Alright, so what this graph's going to look like, the first point I'm going to plot is an asymptote. So at 1, because it's cotangent, it's an asymptote. Then I'm going to follow the pattern of the parent function. My cotangent parent function, my next point was high. Middle low, asymptote. High critical point, middle critical point, low critical point, and at 17 I would have an asymptote, but I'm out of space. So this is almost 2 whole cycles of my cotangent function. So again, it's just finding your x-axis, finding your y-axis, very similar to the way we did sine and cosine graphs. It's just a different pattern to follow. Alright, so that's all we have for tangent and cotangent graphs. So now the last two we need to look at are secant and cosecant. So, whoops, that's not what I meant to do. Alright, so secant and cosecant, if you remember, those are the reciprocals of sine and cosine. Secant is the reciprocal of cosine. So what I'm going to do to start off with is I'm just going to plot the points of my cosine parent function. So hopefully we remember this. It had a height of 1. The lowest is -1. It started at the top, and the period in degrees was 360, which means my critical points were at increments of 90. So I'm just going to plot those dots here. So it went high, middle, low, middle, high, middle, low, middle, high. So that's the points of my cosine function. So again, we're going to look at what happens basically when I plug in those x values to that equation. If I plug in 0, the cosine of 0 is 1. The secant of that, a secant of 0 is the reciprocal. So it's 1 divided by 1, which is still 1. So that is still a point in my graph. Now if I plug in 90 though, the cosine of 90 is 0, which means the secant of 90 is the reciprocal. And we just talked about with tangent and cotangent, that reciprocal is undefined. Alright, the cosine of 180 is -1, so that is still -1. But again, at 270, the reciprocal of 0 is undefined. So I need to see what happens on my graph as I approach that undefined value. So again, I'm going to go back to my calculator in order to see what's going to happen here as I get close to 90. And my calculator does not want to clear. There it is. So let's say as I approach 90 from the left, I type in secant as 1 divided by the cosine of, let's start with 89 again. 1 divided by the cosine of 89.9. And if you guys can see, this is starting to do the same thing as my tangent graph did. As I get closer and closer and closer to 90, these values, whoops, I meant to do, these values get closer and closer to infinity. They just keep on getting bigger and bigger and bigger. Same thing if I look at the other side. 1 divided by the cosine of 90.1 is a large negative value. 1 divided by the cosine of -0.01, a larger negative value. So very, very similar. So that means what I'm going to have is an asymptote again at 90. And what makes these very, very easy to graph then is as a result, all of those values that would be middle points, that would be 0 for secant and cosecant, are just going to be asymptotes on the reciprocal graphs. And if you look, what happened as I approached those asymptotes, it went either up towards infinity or down towards negative infinity. So what this graph is going to look like is a bunch of little parabolas in between asymptotes. And what's going to make these really, really simple to graph is the points that I'm using are just the same as a cosine function to begin with. So essentially, all I have to do to graph a secant graph is to plot the points of the equivalent cosine function. But the difference here is instead of plotting middle points as middle points, all those middle points turn into asymptotes. And those high and low points, instead of being high and low points, those become the vertices of parabolas. So all I need to do is graph the equivalent reciprocal function, plot those points. It's just I'm not going to connect the dots. Instead of connecting the dots, I'm going to turn middle points into asymptotes, high and low points into parabolas. So we're going to use that idea to graph the cosecant parent function. Alright, so the cosecant parent function, that is the reciprocal of sine. So what I'm going to do is I'm going to plot the points of my sine parent function, and we'll do this one in radians. And if you remember the difference between sine and cosine, which will also be the difference between secant and cosecant, sine graphs start in the middle. And we use different colors, it's a little easier to see. So I've plotted the points of my sine parent function, but in order to turn this into a cosecant graph, everywhere I plotted a middle point, it turns into an asymptote. And now I take those high and low points and just turn them into parabolas. And that's how I draw secant and cosecant graphs. So again, if you know how to do sine and cosine graphs, these should be pretty simple for you. But if you're not quite sure and still struggle with those, make sure you look back over how to draw sine and cosine, or else you're really still going to struggle with secant and cosecant.